Hello everyone, my name is Nikhil Gupta and today I'll be talking to you about forecasting the next recession. Our team consists of Stuart Miller and myself. By some definitions, a recession is defined as 2 consecutive quarters of GDP decline. So we are going to build a model to predict the GDP for the next 2 quarters. Our dataset consists of the GDP for USA from 1982 to 2019. We also collected about 20 macroeconomic exogenous variables which could potentially impact the modeling of the GDP. We started off by building a univariate model for our dataset. So first we needed to determine if the data was stationary. So looking at the realization, we see that there is a slight downward trend in the data, and that is evident from the spectral density, which shows a peak at f equal to 0. But this peak is not appreciable and does not warrant doubting the stationarity of the dataset. Looking at the variance, we see that the variance is fairly consistent throughout the dataset except for a couple of excursions. But again, since we only have one realization, it's very hard to determine if the variance varies with time, and there's not enough evidence to doubt the change of variance with time as well. Looking at the third condition, we find that the ACF for the first half of the data is quite consistent with the ACF for the second half and also consistent with the full data set. So in all, there is not enough information to doubt the stationarity of the data set, and hence we'll proceed by modeling this as a stationary data. For the model ID process, we use the AIC and BIC approach. Both AIC and BIC gave an ARMA 2.0 model as the best fit model. On finding the estimates, we found that the dominant root had a positive phi, which is quite consistent with the exponentially decaying ACF that we saw previously. The model had a white noise variance of 5.6. To evaluate the model appropriateness, we looked at two factors. First, we looked at the residuals and found that these were quite consistent with white noise, except for this sharp dip that we see here. The ACFs are also quite consistent. There were a couple of ACFs which exceeded the 95% limits, but this is quite consistent with what you would expect from white noise. The Young-Pox test also failed to reject the null hypothesis at k equal to 24 and k equal to 48. Hence, we can conclude that this model is quite appropriate. We also looked at the realizations for this model, and we found that this tends to mimic the actual realization quite well. It shows the sharp rise and the sharp dips in the GDP value, and the ACFs and the spectral density for this for these multiple realizations also seem to be quite consistent with what we see for the actual GDP realization. Next, we looked at the model performance. For this, we use a batched AC approach where we use data from 4 years to predict the next 2 quarters. The forecast from the ARMA model seem to track the movement in the data quite consistently. The only thing that they didn't do well is track sharp dips in the GDP or sharp rises in the GDP, which can be seen by these spikes in ASC. The spikes is mostly appreciable when there's a sharp dip in the GDP value. Next, we moved on to the modeling of the VAR model, which is a multivariate model. So for this, first we did a cross-correlation analysis, and we found that there were several variables that were highly correlated with the variable of interest, which was GDP change. They were mostly related to number of jobs in the economy, business-related information such as inventory and the pricing index, and also treasury information, interest rate information, and things like that. What was also interesting was that most of these variables showed the maximum correlation at lag equal to 0. What this means is that we may not have to use too many lags in our multivariate model when we eventually build those models. So for building the VAR model, because we had 20 exogenous variables, we couldn't really use all the variables in the VAR model because it would lead to overfitting. So we had to come up with some way to reduce the number of variables to use. For this, we used the var select process and the BIC selection criteria to find the maximum lag to use for various trend types. And you can see for all the 3 trend types, var select recommended to use a lag of 6. But when we built the model with lag equal to 6, we found that only 4 of the exogenous variables showed significance, and that too only till a lag of 3. For the other 2 trend types, we only had 2 variables that showed significance till a lag of 6. Now, because the number of job change was also one of the top variables in our cross-correlation analysis, we decided to use this reduced set of variables to rebuild these models with these reduced set of lags as well. Next, we looked at the performance of these 3 models. What we found was that the model with trend equal to none and trend equal to just trend did not perform very well. In fact, if you look at the forecast here, they tend to have very large excursions, and that can be seen from this ASC plot as well. So the model with trend equal to both, which consists of both the constant term as well as the trend, seem to perform the best, and we will only keep this model for future analysis. Next, we evaluated the residuals of this model, and we found that this is quite consistent with what we would expect from white noise. Although there are a few excursions here again by this sharp dip in the GDP, the ACFs are also quite consistent, although there is a couple of excursions. So we feel that this model is quite appropriate, and we'll keep this for our final model analysis. Next, we moved on to the neural network modeling. To find the best set of hyperparameters, we used a grid search approach where we varied the number of hidden neurons, the number of repetitions, and whether or not to detect seasonality across a random grid of size 5. We found that the default setting did not tend to do very well. In fact, the setting with only one hidden neuron, 13 repetitions, and seasonality detection set to false did the best. And similar to the previous multivariate model that we built, we found that the number of lags that this model selects is quite consistent with what we found previously. In fact, the maximum lag selected is only 4. Looking at the residuals of this neural network model, we find that this is quite consistent with white noise. The ACFs are also not showing many excursions, and this is in fact even modeling the sharp dip in the GDP very well. So now that we've built the three base models, let's look at their performance together. We find that the autoregressive model tends to perform the best. It has the lowest mean and lowest median for the ASC value. We find that the neural network model tends to predict the sharp dip in the GDP the best, as can be seen from this forecast plot as well. And we find that the VAR model actually performs the worst from these three models. Next, we build ensemble models using these base models. We built two naive models using the mean and median of the forecast, and one with a linear regression model that combined all these three models together. We found that from the base models, the AR2 model tended to perform the best, and from the ensemble models, the generalized linear model tended to do the best and actually improved the performance over the AR model slightly. So in conclusion, we found that the GDP data was very noisy and the base models didn't really capture the true variance in the data. Of the base models, the AR2 model tended to perform the best, with the ensemble model improving the performance slightly. But since we only had 2 data points in our test data set, we might want to evaluate this further. In the future, we might also want to include more exogenous variables to see if we can improve the performance. That brings us to the end of our presentation. See you next time.